Welcome back. We are in our review of Chapter 1 in Unit D. So the first lesson we did we spent a lot of time looking at different charts and graph of what's happening with globally with energy consumption. And also we looked at a lot. We took it down to the Canadian level. We also looked at the Alberta level, and we took a look at energy versus electricity, and then the types of energy and electricity. Some of the key things that you need to be able to know is like the difference between the global energy consumption in the past versus the present. Okay. And that we have seen in the past here. It's growing exponentially. So you can see in this chart, this is exponential growth. Okay. Which is matching our human population growth as well. Okay. You also will see that in early on in the 1800s, before the Industrial Revolution, the majority of the energy consumption was biomass. And when we talk about traditional biomass, we're talking about fuels like burning wood, that kind of thing. Okay. And then that changed with the Industrial Revolution right around here. And you can see a dramatic change in the variety of different fuel sources, especially the fossil fuels, the gas, the oil, and the coal. All right. So those are the main key things that you need to understand from that graph. Okay, so you also need to take a look at Canada's per capita energy consumption and compare it with developed and developing countries. And then talk about some of the factors that might be the reasons for this difference. Okay. So you might remember seeing these two charts before, where you can see from these charts, if you compare the population in the year 2000 of the developing countries with the developed countries, the developing countries had a much higher population percentage, right, of the population. So 5 billion people were living in developing countries, whereas only about 1 billion lived in a developed country like Canada. Okay. But if you look at the energy consumption, which is this, for that same time period of year 2000, those developing countries with the 5 billion people only used 32% of the energy, where they should have used about like 5/6 of the energy. So closer to it should be closer to 90 something percent, right? Whereas the developed country use 68% of the energy. So each person in that 1 billion here was using a lot more energy. So much higher per capita. There it is. Much higher per capita usage in those developed countries like Canada. I think on the next page, does it talk about that? Oh, maybe not. But some of the reasons for that higher usage is a lot of times industrialization. So the number of the amount of product that's made in a country. Also, if you have a lot of the oil industry or energy industry, a lot of industry. Oh, I lost my pen here. Also, colder climates, more wealth, so greater GDP of a country. You'll have more people have vehicles, right? Vehicles, transportation. If you have cold, you're heating up many more facilities. There are lots of different reasons for energy consumption. Okay, so we're going to apply the concept of sustainable development to increasing the efficient use of energy. So sustainable development, we have our definition here, can be defined as development that meets the needs of the present without compromising the ability of future generations to meet their needs. Okay, so one way that we can achieve sustainable development goals is to increase the efficiency of energy devices, or the efficiency of what we're using. Another way that we're going to explore in the next section is using more renewable energies, right? So if at present we're not using up resources that are limited, so non-renewable energy sources, then our future generation will still have the ability to meet their needs. Okay. Every time we use energy, some of it is transformed. Some of the transformation is some of this energy transformation is into useful energy output, and some is lost as heat or other forms of energy that we might not want, like light or something else, depending on sound. Understanding and improving the energy efficiency of a device is one way we can reduce our energy consumption. So you use this equation, the percent efficiency, where you always put the output energy, or also known as the useful energy, that the device is meant to transform and create, over the output. So this is the total amount of energy you had to put into the device. Okay, and then multiply by 100. All right, so a couple example questions based on that lesson 1.1 information. Which of the following graphs represents the world's use of energy over the last century? You should be choosing the exponential growth. So it's increasing over time, right? There's your time, there's your energy use, and it is increasing over time. Right? It's going up dramatically. And it's not just increasing linearly, that's what that graph is. Okay, it's increasing exponentially. And so you could predict, if you're looking in the future down here at say 2040, your energy is going to be way up higher. So that's, if you need to predict, you just extend that graph and then come down to your x-axis and figure out what the reading is. Or you can go across to your x-axis if you need, y-axis if you need to figure out that reading. All right, the highest energy use per capita tends to be in areas of the world that are not the highly populated, right? Tends to be the developing countries, heavily industrialized, have large geographic areas, of warm average temperatures, but the heavy industrialization uses a lot of energy. You have a lot of industry, you also have a higher GDP, so there's a relationship with GDP. All right, it's another example. The electricity generated by energy source for a particular country is represented by the pie chart below here. The total percentage of energy generated from renewable energy sources is, okay, so we're just looking for renewable, so not oil, not natural gas, not coal. Wood is considered renewable because we can just replant trees. Hydroelectric is using water, and not nuclear. No, it is not considered renewable. So just these two, and that's where the 16% for your answer is coming from. All right, another example question. This is on efficiency. The power plant provides an input power of 450 megawatts to transmission lines, and if the long distance transmission of the power is 92% efficient, then the power output after the transmission is blank. So we're going to write our percent efficiency calculation. Formula is the input energy, and this is in your data booklet, divided by, nope, my bad. Right, so it's actually the usable output over the input energy times 100. And we've got 92% efficiency here. We know that the input is 450. They even tell us it's called input. So we've got 450 megawatts. I'm not going to worry about the units. Whatever the units are going in are going to be the units coming out. So this is our X that we're trying to find. And then we're going to multiply by 100 on this side. So to get rid of the 100, I'm going to divide both sides by 100. Divide by 100. So we get 0.92 equals x over 450. And then 0.92 times 450. So x is equal to 414. And then I look back to see my units, and it's megawatts. I hope when you're doing these questions, you don't just watch me do them, you pause it, think about the question before I do it, and then you look at the answer, or try and answer it before I do, and then go back and check your answers. All right, lesson 2, we go into looking at coal and some other fossil fuel energy sources. But we also noted that the original source for all these next energy sources is the sun, right? So we know the sun, it does a lot of things for us, and it creates our wind. So there's a few things that you want to make sure you understand from this diagram here. First off, inside our sun is nuclear reactions. So all the energy is coming from our sun, which the original energy reaction or type of energy is because of a nuclear reaction. Okay, so when the sun's rays come in, about 23% is driving the water cycle. And this is the other important number to know. 0.023% is captured by photosynthesis. And it's this energy that's captured by photosynthesis that we're interested. So that's a very small proportion of the sun's energy is being captured by photosynthesis. But keep in mind that is what is going to, for biofuel, if you're like biomass fuel, burning wood traditionally, but also if we're talking about coal, right? So first off, wood is probably it's probably the most well-used type of fuel. You've probably all had a campfire. Humans have been harnessing this chemical potential energy in wood for a long time to cook and for warmth. The light and heat has kept us and enabled the First Nations people to inhabit all these regions around the world. Especially in Alberta, especially northern Alberta, northern Canada. And it's still today one of the least expensive and most accessible forms of energy in developing countries. Often this wood burning can be a little bit dangerous and not so good for health or the environment, but it can have a lot of incomplete combustion, and so you would never want to have like a campfire in the middle of your house without good ventilation, because you can get that carbon monoxide produced when you have incomplete combustion. Okay. But wood is considered a renewable energy source because it can be replaced in our lifetime in a short period of time, so it's considered renewable. The next fossil fuel, or the next fuel source we looked at, the first fossil fuel is coal. And this is the energy that was stored in plants, and it was passed on to animals, and then eventually the animals and plants died. And over time, the sediments got compacted over time, and with lots of heat and pressure, you will form these fossil fuels over a long period of time. And that's why these are considered non-renewable energy, because they take millions of years to form. Okay, they will not be replenished in our lifetime. You also need to understand natural gas is another very common fossil fuel that we use, and methane is the main hydrocarbon in there, but there are some other hydrocarbons. And again, it is a fossil fuel, so it's from animals dying, and then over time, the pressure and sediment and rock build up, and the gas that they turn into is captured in the rock layers. Okay, so how are these fossil fuels used to create electricity? Well, we can take the fossil fuels and burn them in our cars, yes, but we also need electricity. So you do need to make sure you understand the coal-fired power plant. If you haven't watched a video of that, make sure you do. But the basic concept is, first off, the coal is burned. So the coal is put into a burner. It's burnt, and you can see cold water coming in to the burner, and that cold water is heated up and boiled. And when it boils, it goes into steam, and the steam is what's released, and that steam causes the turbine to turn. Okay? And then that water condenses, cools down, drops back, and is reused. But the important part is if you turn the turbine, it's connected to turning the generator. And we learned back in Unit B, I think it was, C, that the generator is basically you're turning coils inside of inside of a magnetic field, so you're inducing a current, and that current is electricity, and that's being sent off to users. Okay. So this turning a turbine generator to users, this part of the cycle is common to most plants that create electricity. Okay, as you're going to see repeatedly turbine generator to user electricity. Okay, and you should make sure you understand the changes that are happening in the energy conversions. So in the coal you have chemical energy, which is burned to create the thermal energy, which then the steam turns the turbine to mechanical energy, which gets all the way to the generator, which creates the electrical energy. You can actually go back even further. The original source of coal, right, is animals, plants, which are chemical energy. But even before the plant gets its energy from the sun. And in the sun, it's nuclear energy. So the energy conversions are actually from the sun, the nuclear energy, and then the plants store it as chemical energy in their cells. Alrighty. Yeah, so we just did this. There's another example. Oh, but this is also including some of the different particulates and byproducts of coal-fired generating plants. We're going to talk about this in a summary a little later again, but make sure you remember all these different pollutants that are coming off of a coal-fired plant. Alrighty, what do we need to know here? You do need to know combustion reactions. Remember, need oxygen, and they always release carbon dioxide and water if you're burning a hydrocarbon. This is on page 9 in your data booklet if you ever forget it. And you do need to remember that a combustion reaction is always exothermic because energy has to be released. We need that energy released so that we can heat the water in our plants, our power plants. All right, Hess's formula. Hess's formula can actually let us figure out how much heat, right? We want to figure out how much so that we can see how much electricity eventually we could form. So we use Hess's law to predict the heats of combustion, the amount of heat that's released for a formula, for a specific substance. This is on page 5 of your data booklet. So remember, with this formula, you probably have lots of experience with this. You're going to take the heats of formation for each of the products, multiply each one by the number of moles in the balance formula, and then you're adding up all those product heats of formations. And then you're going to subtract all the heats of formations for the reactants, making sure that you multiply each reactant by the number of moles. Okay? All of this is going to end up being in kilojoules in the end. All right, so there's an example calculation here. I want you to pause the video and see if you can create the balanced equation for the combustion of glucose here. All right, hopefully you've balanced your glucose so that you can just compare that to the answer here. So whenever you have combustion, you're always going to be reacting with oxygen gas. And in a hydrocarbon reaction, you're going to be always creating carbon dioxide gas, and we're going to assume it's water vapor. We're going to assume this is not happening in the body so that it's hot and the water vapor is released. Okay, so we always want to balance in the same order. Carbon first, then hydrogen, last oxygen. So there are 6 carbons here, so we're going to need 6 carbons on our reactant side. Then we're going to look at our hydrogens. We only have 2 over here, but 12 on our reactant side. So I'm going to put a 6 in front of the water. So I have 6 times 2 gives me 12 hydrogens. Now we add up all our oxygens. So on this side, now this is where you got to watch out. So our 6 here multiplies by the 2 for the oxygen. So we have 12 oxygens here. And this 6 multiplies by the oxygen, which is just 1. So 6 oxygens there. Okay, so we have a total of 18 oxygens on our product side. We have 6 oxygens there and 2 here. The only place we can change the number of oxygens is in front of this oxygen that's reacting in the combustion reaction. So right now I have 6. I'm going to take 6 away from our 18. So I have 12. Take away 18. I'm going to take away this 6. So I need this to be what number? Okay, so I have 18 in total. I need to have 18 on this side. I have 6 here. So I need to take away the 6 from 18. So I need these oxygens to equal 12. What number do I have to put in front of the O2 to get 12 here? It's going to be a 6. So if I go 6 times 2 gives me 12 oxygens. We're just double checking. And then we have 6 oxygens here. And that gives us a total of 18 oxygens. If you didn't catch that, make sure you go back and just rewind and make sure you understand how that's balanced. Okay, so this is a long version of this kind of Hess's formula where you actually have to balance the equation first. A lot of times you'll get the balanced equation, or you might have to do it as 2 separate questions. All right, so let's do this. You're going to need your data booklet and your heats of formations in your data booklet. So you're going to be using your data booklet, page 5, all those heats of formations. If you don't remember how to do this, make sure you go back to lesson 1.2 and do some review. I did quite a few example questions in that, so you might want to check out some of those videos because I am going to go reasonably quickly. I also don't have the chart here on this, but again, I suggest you pause this and see if you can use the Hess's law formula and get the right answer. Okay? And then come back and check. All right, so hopefully you've gone ahead and done that. So we have our products. So we're going to look up the heat of formations for our products. So we've got carbon dioxide gas. So I'm going to look on my chart for carbon dioxide gas, and it is negative 393.5 kilojoules. And I'm just going to leave out the units for now. And I have 6 carbon dioxides, so I'm going to have to multiply that by 6. I'm going to add that. Okay, so I'm going to put these in big brackets. I'm going to add that to my water gas, which has a heat of formation of negative 241.8 kilojoules. And there are 6 waters. So those are all my heats of formations for my products, each one multiplied by the moles. I'm summing them all up, adding them all up. Then I'm going to subtract the reactants heats of formation. So I'm going to look up glucose on my chart now, and I see glucose. Ooh, glucose is huge. Negative 1. 1,273.3 kilojoules. And there's just one glucose, so we don't have to multiply. And then we look up oxygen, and there's no oxygen. Remember, no oxygen on the chart. It's an element, so it's just 0. So we can put a 0 there if we really want, but we don't need to worry about it. Okay, so we're gonna add up all the products first here. So pause this and check this on your calculator. Make sure you're doing this reaction right. Okay, so as you can see, I've multiplied the 6 into each of these heats of formations, and these are the numbers I get. So if you didn't get those numbers, try again. And then I'll show you the next step. It's best to do these in steps. Okay, and the next step, I just add these 2 negative numbers together, so I get an even bigger negative number. And now I'm going to subtract my reactants. All right, so overall, my answer is negative 2,538.5, and the units are kilojoules. Okay, the negative tells us this is exothermic, so that's how much heat is given off when 1 mole of glucose is burnt. Okay, so we could capture that energy as it's being released from the reaction, from the combustion, and that could be used to heat up water, that turns the steam, that turns the turbine, that's connected to the generator to produce electricity. All right, so one of the key things you need to remember about burning fossil fuels is that it releases carbon dioxide, which contributes to climate change and the greenhouse effect. There's a little bit about greenhouse effect here. The effect on global temperatures are increasing and the sporadic weather patterns. So some of these effects of burning fossil fuels, the glaciers are melting, more water and flooding, the ocean levels are rising, we've got changing vegetation, and species are going extinct at very high rates, correct? currently. Some of the solutions to whether we want to burn carbon dioxide or methane. We're not actually burning. Well, yeah, we are. If we're burning methane, we can still get carbon dioxide being formed as well. But anyway, sorry, methane is even a stronger greenhouse gas than carbon dioxide, so we have to even be really more careful about it, even because it's that much more damaging. So some of the solutions that we had here are driving less, replanting trees or reforestation, carbon capturing or sequestering, you've probably heard that term before, or investing in alternative energy sources, which is what you're going to be examining in the second chapter. All right, so some of the advantages and disadvantages of using coal fire plants. First off, the cost. Why do we use it? It's because it's cheap, it's affordable, and abundant. It's like, we have tons of it in Alberta, and that's one of the reasons we have been using it for so long, because it's right there, it's easy to use. It's very reliable. We know the energy yield that we're going to get with it. We know you burn so much, you're going to get so much energy. And it can be made cleaner by removing the carbon if you carbon sequester, or taking out the sulfur. But coal is considered a non-renewable resource. That means it will not be replenished in our lifetime, or humans' lifetime, probably, that fact. It produces sulfur dioxide, carbon dioxide. Remember, sulfur dioxide affects acid, or causes acid rain. Carbon dioxide causes global warming, or the greenhouse effect, climate change, and other environmental destruction. All right, so there's an example question here. I am not going to do another Hess's Law, but I suggest you give this one a try. This is basically a question. Okay, I'll just read it for you here. The methane gas is collected from decaying organic waste and burned to produce heat and electricity for waste treatment plant. The combustion of methane is represented by the equation below. So it says the energy released from the combustion of 1 mole of methane. 1 mole of methane is, okay, so first thing I want to look and see is I need a mole of methane, and that is exactly what my equation is balanced for. It's balanced for a mole of methane. I want you to try doing Hess's Law right now and see if you can get to the answer. I am going to also do a video of that real quick, put out the answer here so that you can see the solution to this question. All right, hopefully you went and try this one. If you set this up correctly, here's your formula where your heats of formation of the product minus the heats of formation of the reactants all added up. So your carbon dioxide is here, and you have 1 mole of it. Your water, vapor, or gas is here, and you have 2 moles of that. And then your methane, you're going to subtract the methane heat of formation, and you have 1 mole of that. And oxygen is 0, so we ignore it. Okay, just doing the next step from the calculation, multiplying my 2 times 3, negative 393.5, and have that here. All right, I'm also going to point out that 2 negatives like that is the same as a positive. That's what I did there. But don't worry, if you didn't do that, you'll still get the same answers. So we have this. And let's just add or take away negative 74.6, and our final answer should be 998.2. Remember, the units are kilojoules, and this is exothermic. Again, that amount of energy is being released when 1 mole of methane is burnt. That's the end of the first half of this unit review. The last half is all about lesson 1.4, which we know was a much larger unit, part of the chapter on nuclear.